Welcome to the lecture of Renewable Energy System. In today's lecture, we will discuss about the wind turbine types and its history. Wind energy was one of the first known animal sources of energy to be used by early civilization. It is thought that wind was first used to propel sailing boats, but the static use of wind energy by means of windmills is believed to have been taking place for about 4,000 years. Windmills have traditionally been used for milling grains, grinding spices, paint stuff, making paper, and sawing wood. Traditional wind pumps were used for pumping water in Holland and East Anglia in the UK because they often used identical forms of sails and support structure. They were often are also referred to as windmills. Many early windmills were of vertical types as shown in these diagrams. And unlike modern wind turbines, which are driven by lift force, these were drag-driven devices and relied on difference in drag on either side of the vertical shaft in order to function. However, there is one fundamental difficulty with this simple arrangement. This is to do with the fact that as the pedal wheel is spinning on a vertical shaft and the wind is blowing from one side, and if we view the pedal wheel from the upwind side, it will observe that the pedal wheel on one side of the shaft is able to move with the wind, but on the other side of the shaft, it wants to move against the wind. So, as the wind pressure is the same on the both sides of the shaft, the pedal wheel will not rotate unless something is done to reduce the wind pressure on the side that is tending to rotate against the wind. A wide variety of vertical axis windmills therefore evolved, which used a number of measures to overcome this limitation and are frequently reinvented today. They fall into the following categories. Screened windmills. Our screened windmills employ screens or partial walls around the windmill, which are positioned to screen the windmill sails from the wind during the backward part of the cycle, when the sails are moving toward the winds. The second category is clapper windmills, such as shown in this diagram. The clapper windmills are so called because the movable sails clap against the stop as the rotor turn with the wind. So here it is a stop point where the clapper will stop itself, maximizing their air resistance but align themselves with the wind when on the part of their cycle in which they are moving into the wind, so reducing their air resistance. So at this side, it will face the maximum resistance against the wind, and over this side, they will face the minimum resistance against the wind. In the third type, cyclic pivoting sail wind, they are also similar to the clapper windmills but use a more complex mechanism to achieve progressive change in sail orientation. The pitch angle of each sail is cyclically adjusted according to its position during its rotational cycle and to the direction of the wind. This gives a difference in the resistance on either of the windmill's rotation axis, causing it to rotate when exposed to a wind stream. The fourth type is the differential resistance or cup type windmills, such as shown over here. In this type, the blades are the shape to offer greater resistance to the wind on one surface compared with the other. This results in the difference in the wind resistance on either side of the windmill axis, so allowing the windmill to turn. According to historian, the first machine utilizing wind energy were operated in the Orient as early as 1700 BC. It is mentioned that kings Hammurabi used windmills for irrigation in the plains of Mesopotamia. There is written evidence of the quite early utilization of wind power in Afghanistan as well. It was documented from 700 AD that confirmed that the profession of a millwright was one of high social esteem there. Even today, ruins of these windmills that were running for centuries can be found in Iran and Afghanistan. The world's oldest windmills had a vertical axis of rotation. Braided mats were attached to the axis. The mats caused drag forces and therefore were taken along with the wind. In Persian windmill, an asymmetry was created by screening half the rotor with the wall, such as shown over here. This way, the drag forces could be utilized for driving the rotor. In Chinese windmill, which also dated back a long time, a similar asymmetry is created by sails, which rotate out of the wind on their way back. When they advance into the wind, these Chinese drag wheels dated back to approximate 1000 AD. Similar to the Persian mills, they had a vertical axis and used braided mats as sails. However, in contrast to the Persian mills, they had the typical advantage of vertical axle windmills to utilize the wind independent of its direction. The simplest of this construction can be appreciated in this diagram, which shows a later version of a vertical axis mill with flapping sails. The millstone is attached directly to the vertical driving shaft without redirecting the rotational movement and without an immediate gear. The more recent horizontal axis wind turbines such as the Dutch smoke wheel designed for a higher tip speed ratio that requires a far more sophisticated construction not only for redirecting and back gearing the rotational movement from the horizontal to the vertical axis, but also for the much more complicated bearing of the faster and heavier horizontal shaft. The windmill, like the cup anemometer, belongs to drag-driven rotors with a relatively low tip speed ratio. The simplicity of the vertical axis design is also central to the Savian's rotor and the Darius rotor, but as late Occidental version of the vertical axis principle they utilized partially or exclusively the lift force as their driving power. The Savian's turbine is one of the simplest turbines. Aerodynamically, it is a drag-type device consisting of two or three scoops. Looking down on the rotor from above, a two-scoop machine would look like an S shape in a cross section, such as shown over here. Because of the curvature, the scoops experience less drag when moving against the wind than when moving with the wind. The differential drag causes the Savian turbines to spin. Because they are drag-type devices, Savian turbines extract much less of the wind power than other similarly sized lifting-type turbines. Much of the swept area of the Savian's rotor may be near the ground if it has a small mount without an extended post, making the overall energy extraction less effective due to the lower wind speed found at lower height. Savigny's turbines are used whenever cost or reliability is much more important than efficiency. Most anemometers are Savigny's turbine for this reason, as efficiency is irrelevant to the application of measuring wind speed. Much larger Siemens turbines have been used to generate electrical power on deep water buoys, which need small amounts of power and get very little maintenance. Design is simplified because, unlike with horizontal axis wind turbine, no pointing mechanism is required to allow for shifting wind direction, and the turbine is self-starting. Surveyors and other vertical axis machines are good at pumping water and other high torque, low RPM application and are not usually connected to electrical power grid. The Darius wind turbine is a type of vertical axis wind turbine used to generate electricity from wind energy. The turbine consists of a number of curved airfoil blades mounted on a rotating shaft or framework. The curvature of the blade allows the blade to be stressed only in tension at high rotating speed. There are several closely related wind turbines that use straight blades. There are major difficulties in protecting the Darius wind turbine from extreme wind condition and in making it self-starting. In the original version of the Darius design, the airfoils are arranged so that they are symmetrical and have zero rigging angle. That is, the angle that the airfoils are set relative to the structure on which they are mounted. This arrangement is equally effective no matter which direction the wind is blowing, in contrast to the conventional type, which must be rotated to face into the wind. When the Darius rotor is spinning, the airfoils are moving forward through the air in a circular path. Relative to the blade, this oncoming airflow is added vectorially to the wind so that the resultant airflow creates a varying small positive angle of the attack to the blade. This generates a net force pointing obliquely forward along a certain line of action. This force can be projected inward past the turbine axis at a certain distance, giving a positive torque to the shaft, thus helping it to rotate in the direction it is already traveling in. The aerodynamic principle which rotate the rotor are equivalent to that in autogyros and normal helicopter in autorotation. As the aerofoil moves around the back of the apparatus, the angle of attack changes to the opposite sign, but the generated force is still diagonal in the direction of the rotation. Because the wings are symmetrical and rigging angle is zero, the rotor spins at a rate unrelated to the wind speed, and usually many times faster. The energy arising from the torque and speed may be extracted and converted into useful power by using an electrical generator. The most prominent distinctive feature in the horizontal axis windmills is the rotor with the horizontal axis whose sails rotate in a plane vertical to the wind, just like an aircraft propeller. In that case, our driving principle different from the blade area obstruction of the drag-driven rotor has to operate. The post mill consists of a timber support holding the vertical center post around which the box-like buck, that is, the mill house, turns on a pivot, such as in this diagram. Using a tail pole, the buck together with the rotor was oriented in the wind. So here, this is the moving part, such as over here. This is the moving part. The main shaft with the rotor is almost horizontal. The brake wheels drives via the lantern gear, the vertical shafts with the milestone. Only from the 19th century onward, post windmills were equipped with two lantern gear for parallel milling operation of two sets of millstones. The post windmills was exclusively applied for grinding grains. In southern Europe, the post mill did not gain popularity. Another mill type was widely spread there, the tower mills. Already very early on, the first windmills of this kind were used for irrigation. The first documentation of these mills dated back to the 13th century. Main feature of the older Mediterranean types are the cylindrical stone-built mill house, such as shown over here, a fixed hatched roof and a guy rotor, rotor with 8 or more sails. In this diagram, you can see the roof is fixed, so we cannot change the direction of the rotor. So it is fixed, and these boys or guys, whatever you say over here, they are 8 or more sails. Later version, mainly in southern France, had a turnable wooden cap and a four-bladed wooden rotor like the post mill. So some of the variants are here in which the roof is made from the wood and that can be rotatable. The turnable cap is the main characteristic of the Dutch smoke mill which came into use in the 16th century. It is a further development of the tower mill as the lighter wooden construction of the octagonal tower could be easier erected on the wet Dutch marshland and then the heavy stone construction of the tower mills. In Holland, the Dutch smoke windmills were mainly used for the drainage of the Lauder, often arranged in a series to lift the water mill by mill over the embankment. In the rest of the Europe, they were applied preferably for grinding grains. The last type of historical windmills is the American farm windmills, which is also known as Western mills, which was developed in the mid 19th century. The Western mills was mainly used for providing drinking water for both people and cattle in North America. Moreover, it assured the water supply for the steam locomotive of the new railway expanding into the west. The main characteristic of this windmills is the rotor design of a diameter between 3 and 5 meters, with more than 20 metal sheet blades suited on the top of a metal lattice tower. It uses a crankshaft to drive a piston pump. The Western Mills was the first windmills type with a fully automatically controlled yaw system, including a storm control. So the Western Mills is still nowadays a modern machine of which tens of thousands are installed with a nearly unchanged design in Australia, Argentina, and the USA. In contrast to the modern wind turbine, the old windmills needed the permanent attendance of a miller who was not only responsible for milling but also for the safe operation of the windmill. The main tasks in windmills operation were adjusting the windmill rotor to the wind direction, lifting or reefing the sails according to the wind speed for power control, and braking the rotor early enough when a storm was growing. Only the Western mills was the first type without need for an operator. The adaptation of the power consumption by the rotor to the prevailing wind direction was far more crucial. For this purpose, more or less sails was on the sail frame of the windmill blade. This was a risky issue, especially when the miller underestimated the wind and suddenly a strong breeze or even a storm came up, and there was the danger of an overspeeding of the rotor. Then, to reef the sail completely, the miller had to brake the rotor as fast as possible using a wooden brake acting on the wooden gear wheel. Due to excessive friction heat, many windmills burned down because the miller had started braking the rotor too late. Therefore, the invention of the spring sail, which were easily controlled by a lever, brought a significant relief for the millers. They allowed braking the rotor even during a storm because even under full operation, the shutter of the spring sails could be opened completely from inside the mill house so that the wind could blow through the blade surface. The discovery of the blade twist was most relevant for an increase in the rotor efficiency. This innovation was studied by John Symington, who presented the result of his wind rotor experiment to the Royal Society of England in 1759. With a sophisticated test rig, which nowadays is replaced by the wind tunnel, he verified and improved the existing rules of windmill construction. He recommended a blade pitch angle between the blade and the rotor plane of 18 degrees at the rotor hub and 7 degrees at the rotor tip. He also found out that for a given rotor diameter, an increase of sail surface beyond a certain surface size no longer increases the rotor power output. Moreover, Symington determined the power and the tip speed ratio, the ratio of the circumferential speed at the tip of the blade to the wind speed, whose value were in the range between 2.2 and 4.3. With the development of the Western mill in the 19th century, a completely new era began for the application of wind energy. It reflects the industrialization of the wind energy application. The Western Mills was not only the first wind turbine in industrial series production and made from metal, it was the first wind turbine with a completely automatic control requiring no supervision by a human operator. A sophisticated system of wind vanes served for yawing and protecting against overspeed during stormy weather. Paul Lacour, professor at the Espoo School of Engineering in Denmark, investigated since 1891 systematically the application of wind energy for electricity generation and noticed at once that due to its low tip speed ratio, the Western mill was not very suitable for this purpose. He developed a very perfect self-governing four-bladed wind turbine with a DC generator for remote homes. During the First World War, more than 250 turbines of this type operated in Denmark. For more than 50 years, these Lacor machines were produced. The first wind turbine generator for electrical power generation that supplies to the grid was developed by the engineer Palmer C. Putnam, and the manufacturer of the wind turbine is Smith. The turbine has the capacity of 1250 kilowatt with the rotor diameter of 53 meter. In 1941, this turbine started operation and was running with 1000 operation hour until 1945. The cost of produced electricity energy during this testing phase were 50% higher in comparison to conventional energy production. According to this result, Palmer stops his improvement of this turbine. In Dharma, Johannes Joule gives the distinction of the development for the coming years. His primary target was a resiliently designed energy supply to the grid. The Getzer turbine with a capacity of 200 kilowatt and rotor diameter of 24 meter is characterized by these features such as asynchronous generator, simple rotor design with covered plywood, aerodynamic brake using the stall effect, and first stick brake as additional brake. In the 60s, the development stopped according to the cheap imported oil. According to steam rising price of oil in 1973 and 1978, wind energy has a comeback in the mind. In Europe, different countries waste millions into the development of large wind turbines. The Grauwein from Germany was supported with millions by the German government. It was a two-bladed turbine with 3 megawatt capacity and 100.4 meter rotor diameter. Most of these projects were ahead of their time and failed, while the large projects collapsed in Denmark, causing a new market of small turbines to emerge. Small turbines with rotor diameter of 12 to 15 meters was manufactured for agriculture engines produced by Vestas and Bonus. Since 1982, the size of the wind turbine progressively increased, both in rotor diameter and electrical power. In 1982, the rated capacity of wind turbine in average was 1 megawatt with 25-meter rotor diameter. In 2004, this has reached up to 5 megawatt with rotor diameter of 125 meter as well as tower height about 150 meter. A brief introduction to early wind turbine system is presented here. The first wind energy system exists in ancient civilization in the Near East Persia, where windmills was vertical axis. In the Middle Age, post mills was introduced in Northern Europe, which are mainly horizontal axis windmills. Windmills in US in 19th century was windrows horizontal axis type as shown in the diagram and mainly applied for water pumping throughout rural America. In 1888, Charles Brush built first large-size wind electricity generation turbine with 17-meter rotor diameter in windrows configuration. The capacity of the generator was 12 kilowatt. In 1890s, Lewis Electric Company of New York sells generators to retrofit onto existing windmills. Between 1920s to 1950s, propeller type of 2 and 3 blade horizontal axis twin electricity conversion system was introduced. Between 90s to 40s, between 1940s to 1960s, rural electrification in US and Europe using oil leads to decline in wind energy conversion system use. During this period, electricity system has become very competitive, and electricity was generated by several other means such as fossil fuel. At that time, the awareness about the environmental effect was low. Thus, the key attribute to prefer the source to produce electricity was the scale of installation, that is, how much power can be generated from a single unit, commercialization, competitiveness, and ease in the grid integration. The progress in green energy was made after 1970 crisis, and the catalyst for progress was economic, energy independence, and environmental benefit. Now, wind energy system is reaching its maturity. Turbine standardization has been established. As a standard, wind turbines having three blades in upwind direction and a horizontal axis on a monopole tower. In today's lecture, we have discussed the different types of wind turbine and their history. Today's lecture ends here. Thank you for listening.